So, what we have here is differentiability. What we are trying to do is continuity. Where we are going is that limits f of x as x tends to a is equal to f of a, right? Okay? Or, to prove this, it suffices to prove that. Agree? Agree? So with this, and because what did you mean when you say something is differentiable? We mean the left and right is guaranteed. So if the left and right is guaranteed, it simply means I can say that f prime of x at a value anyway, I can change that. This limits of f of x plus h, no, a plus h, something like this, minus f of a, okay? If this is x, of course, then I can say as h tends to 0, sorry, divided by h. Is that not? That this limit exists. So if it is differentiable, this limit exists. So if you look at it, we're going to try to do some manipulation by saying f of a plus h minus f of a, this limits, sorry, I forgot the limit part. We're going to start by simplifying this limit. This limit will be equal to, as h tends to 0, sorry, this limit, if I can work this limit, because this looks like this, one way or the other. Can you see that? So that's the reason I'm working towards this, one way or the other. Hello? I'm trying to work towards it. That's why I started from here. It's like you're looking at the end point. But of course, your beginning must make sense. So what you are given, the fact that this thing is differentiable, could be the beginning of your proof, or it could be something you use along the line. But your continuity to be proved must be the end product. If I want to write that it is continuous, it means I already established that it's equal to 0. So I'm not establishing that it's equal to 0 here yet. I'm going to try to simplify it. I'm going to make sure it looks like that, and it is equal to 0. Then I can justify that, yes, it is continuous. So watch what I'm going to do. So this limit is the same when I say h tends to 0. Remember, this has no h or anything, right? Then I'm going to say f of, because I want it to look like the continuity that we did. Can you see that? Now, h cannot escape because it is the variable to which it is tending to 0. I've chosen h because I want it to look like the differentiability that we are talking about. All right? But for the continuity, the variable will have to change to x. So you have to learn some of these manipulation skills. Now, because my limits, we can have product. Okay, when you have product, limit or product of two functions is actually the product of their limits. Do you agree? Then we can change this to limits, h tends to 0, f of a plus h minus f of a divided by h times limits as h tends to 0 of h. Do you agree? Now, does this limit exist? Why? Speak louder. Say that again. Because? No. Does it exist? It's not because we need to prove something. What you're trying to get is not the reason for the existence. I'm saying, we know that this can be easily found, right? But this one cannot be easily found. We don't know what it is. But my question is, does it exist? What does this mean? What? This means, I'm saying, this means the derivative, right? But does it exist? Because if it does not exist, it means everything we are trying to do does not exist. Are you getting what I'm saying? This is the derivative. It's like the gradient of the chord. This is the gradient of the chord, remember? Okay, this is the gradient of the chord. And the limit of the gradient of the chord gives you actually the gradient of the function. Are you with me? The gradient of the function at point what? Do you understand? Do you remember this? So my question is, does this exist?
Yes.
Yes. Because what? The function is differentiable. Are you with me? Why the other part is just 0? Direct substitution. Limit of h as h tends to 0, that's 0. I start again. We start by simplifying this limit. Why did we choose this? We want something that will look like this eventually. Okay? Then, to make it look like the derivative function or the gradient function, you know you need to have some divided by h. But you can't just change the question. So you multiply by h, such that you're actually multiplying by h over h. Are you with? And h over h is 1. Okay? So, you can split it by the laws of limits. Okay? The other part is not a problem. You can evaluate that. So that limit exists. H is just a straight line. That is the function h. Are you with me? And the limit exists as h tends to 0. So if this is the curve, right? This is the line. As it tends to 0 from here or from here, as x tends to 0 from here or from here, when I say x, I mean the h itself. Understand? As it tends to 0, this function comes to 0 also. So yes, this limit exists, either from below or from above. Do you understand? So this exists and is equal to 0. But we don't know if this exists, because these are just f of something. We don't know how they are defined. And how they are defined will tell us if that limit exists or not. But something in the question already told us that yes, this exists. But it never told us what the value is. And frankly, we don't care what the value is. We just want to know if it exists. Because we don't need the value. 1 is 0. So whatever this value is, everything is 0 anyways. We only need to know that we can write this. You cannot write this unless this is guaranteed. Because this is equal to this. Do you agree? But you cannot say this is equal to this unless this actually exists itself. This is like a value. Am I making sense? But so the existence of this is from what you are given in the question. That function is differentiable. So if it is differentiable, it means the derivative function exists. And at that point, it will be a value. Am I making sense? Okay? So with this is equal to 0. It means the original from the beginning. So this implies that everything here is equal to 0, right? Can you see at the beginning I never put this equal to 0. I only started from here and I make sure I got 0. So this implies that the limits as h tends to 0 of f of a plus h minus f of a is equal to 0. Agree? Which implies that limits as h tends to 0 of f of a plus h is actually what? F of a. Still doesn't look like what we want. Let's x be a plus h. But even if we change this to x, the limit here should be in form of x also, right? How do we do that? Then, as h tends to 0, which is the initial condition, where does this x tends to? This tends to what? Say that again louder. A. If h tends to 0, a plus h tends to a. Which is more or less a plus 0, which is a. Do you agree? So what are we saying in essence? That x tends to what? A. Do you agree? Or maybe I can write it directly from here. As h tends to 0, x, which is equal to a plus h, tends to a plus 0, which is equal to a. So everything here can be changed. This will now become what? Limit h tends to 0 implies x tends to a. F of a plus h implies f of x. Am I making sense?
Yeah.
And you already have your f of a on the other side. And what is this? What does this mean? Say that again. The function is continuous. Therefore, f of x is continuous. Yes, complete it for me. At x equals a. So you can see that the fact that it is differential, no, I should actually put let's x equals to a, b in D. Because you have to specify that you pick that point from the domain. Am I making sense? So let's put the conditions, the reasons, you can write quickly. The reason for this here. F is differentiable at x equals a, and for the second reason, limits of f of x times g of x as x tends to a will be limits of f of x and limit of g of x as x. Maybe I shouldn't use f because f is the question, so I can use g and h. Maybe we could use another variable, another value, b. Can you see that? So these are the two reasons. Okay? Please read the brackets and make sure you understand. These are the two reasons. Actually, only one reason is here. The other reason should be on the other line. Because look, please, I'm making sure nobody's confused. What we did here was just to split the limits. We haven't applied the differentiability clause. We applied it here when we wrote f prime, okay? So those two conditions in bracket, I'm going to split it into two different lines. All right. So always write, okay, like that. Make sure every step is not questionable. This is for this step and this is for this step. First, what time did you sleep? 12. What time did you wake up? That's 8 hours. And you still feel sleepy. It's on your face. I can see you're so tired. You should sleep early tonight. Wait, who did I ask to sleep early the last time? I think it was you.
Me?
Yeah.
Me?
You were the one who slept in my class for the first time. You should give you a medal for that. You're like, what? Nakita sleeps in the class? Oh my God, something is going on here. Maybe the world is coming to an end. Imagine Lillian sleeping in math class. Like, Jesus must be coming the next day. will do the second part using one of the questions on the book. You ready? Let's look at this. So like I said yesterday, please attention, after this we'll get out of this, we'll do some practice in the class. I gave you the worksheet yesterday, yes? So do some practice in the class. Like I said yesterday, let's just have a recap before we move into this. The function is continuous if that limits f of x, continuous at the point, please. That point must not be forgotten. The function f of x is continuous at that point x is equal to a if the limit as x approaches a is actually f of a itself. When we say the limit as x approaches a, we have to consider the limit from above and the limit from below. Both limits must exist and both must coincide. That is what we summarize as limit of f of x is equal to f of that, okay? Now, that's continuity. We also went ahead to say differentiability exists when, number one, it is continuous, when continuity exists. So it is differentiable at that point if, number one, it is continuous at that point. The other condition is that the left-hand derivative and the right-hand derivative of that function at that point must exist and they must be equal. So that's like a two-in-one condition. The second part is like a two-in-one condition. Now, then we looked at it together and we agreed that when a function is differentiable at a point, automatically it is continuous at that point. Even from the definition of differentiability, one of the conditions for differentiability is continuity. So when you say it is differentiable, it must have passed the continuity test. So then it is continuous definitely at that point. And we've been able to prove that in general. We don't have to have specific situation. That's why we prove in general. But the converse is not always true. So the converse is that when it is continuous, is it necessarily differentiable? We are not saying there are no cases where you don't have differentiability. Okay? For example, if you have a function that is differentiable, you can say, oh, this function is continuous and it is also differentiable because you already know it is differentiable, right? But if you only know the continuity, it's not guaranteed that it is differentiable. It's not guaranteed doesn't mean there are no cases where that happens. Understand? So this is one of the cases where it does not happen. And it's question 3 in your textbook. So there will be other questions like this, so you don't have, I just wanted to pick an exercise. prove that this function, absolute value of x minus 5, defined this way. What do we call this? Remind me of the key word. Functions that we write in bits within a certain interval. Yes, sir? Piecewise function. Okay? Prove that this function is continuous at x equals to 5, but not differentiable at the same point. Okay? So, start, draw the sketch of the graph. It's easy to see that way. Okay? Let's draw the sketch of the graph. Clearly, we could see that when x is greater than or equal to 5, so everything is 5, starts from 5. So I'm going to put my 5 maybe here. Okay? Now, x minus 5 is a line with intercept here. Right? So the line is actually supposed to come from here. But this part is not considered. Can somebody tell me why?
Absolute value.
No.
That's x is greater than
Say that again.
x has to be greater than
You only consider this line from x from 5 and above. When you consider this dotted part, it means you're considering 4, 3, 2, 1. Okay? I'm only showing where the line intersects. Trying to imagine if there was no restriction like this, it would have gone this way. It helps to sketch. Understand? And for the other one, you're having a negative gradient with intercept of 5 on the y-axis. Right? So it's like a mirror. And if you know the absolute value function that we did in topic 1, you know it's going to be a mirror, a reflection. Understand? Okay? So this point here is part of this one. So I'm going to draw the other one in a different color. Then it doesn't touch x is equal to 5. Understand? And this is not part of the sketch. It's just for us to be able to imagine. Understand? So this point is 5. This point is 5. So it looks like V. V for Venom. Okay. Now, to show continuity, we need to show the limit is f of 5. This two-sided limit must be the same as f of 5, right? So let's start from limits. So proof. First, the continuity, right? Limits of f of x as x tends to 5 from below. Okay? Now, when it is from 5 from below, is this one. Agree? So we are actually saying the limits of 5 minus x as x tends to 5 from below. You see, there will be different functions for different range of values. Am I making sense? If you look at it from below, as this line, as this x move close to 5 from below, this is moving close to what? Say that again? 0. It's moving close to 0. Are you with me? So, we know that the left-sided limit exists. Now let's look at the other one. Limits as x tends to 5 from above of f of x will be limit as x tends to 5 from above of which function? X minus 5. Because from above, this is, according to piecewise function, this is what you consider. So you change it. Okay? And look at it from the graph. The graph, this is just writing. The graph tells you what to do. So if you are coming from above and x comes here, this is the function. It also approaches what? 0. Are you with me? What is the next thing I should check? F of 5. Remember, the two-sided limit must be the same. This being equal means that that limit exists. But is the limit the same as f of 5? Is another question. Are you with me? That is, without this above and below. Okay? So f of 5 itself because we are dealing with 5, 5 is not in this interval. 5 is here, right? So this is what you use. So that will be 5 minus 5. Okay, we are going to use, so I can put in the brackets from x minus 5. Okay, not from the other one, because both of them will look alike, 5, 5. You get my point? And this is equal to what? 0. Okay? Now, how do we conclude? You can see already, since the limits from below, I keep putting minus 1 like it's indices, okay, of f of x is equal to the limits from above of f of x, and both are equal to f of 5. Okay? If you don't want to write this, you can say, oh, this limit, this 2 implies that the limits as x tends to 5 exists. Because these two are the same. This is the existence of the limits. Are you with me? And since this limit that exists is actually what? F of 5 itself, then what can we say? F of x is what? Continuous at x is equal to 5. Am I making sense? I'm just trying to be more detailed in my explanation. You don't have to be this comprehensive about it. I try to separate the existence of that limit. When we say this limit exists, it means the left and right coincide. If they don't, they coincide. If they don't coincide, it means the limit does not exist. We've discussed that before. Okay? So the fact that the limit exists, is it equal to f of a? Because being equal to f of a is the one that guarantees the continuity. So there are two things here. Do you understand that? So that's why I split it into 2. So you can say that indeed it is continuous. But let's look at the differentiability. Pay attention, please. Now, if I try to write the derivative, okay, differentiability does not exist at that point. Doesn't mean differentiability does not exist at other points. Don't get it wrong. Okay? Now, f prime at any x value, will also be into 2. When we learn differentiation, you don't have to go through this. But right now, just look at it from the graph. For this interval, okay, what is the gradient of this curve, of this line? 1. I'll tell you why I'm not including 5. Or actually, I'll ask you. For this interval, what is the gradient of this line? -1. Can someone tell me why it is wrong to write this?
Because the gradient of at 5 would be 0.
Would be 0. Look at it here. The tangent, sort of, is a straight line. There is no change in y, but there's a change in x at this point. Okay? No, actually, at that point, there's no change in x also. Right? But if you draw like a tangent to it, then you can talk about it, you know. So this is like a turning point. Remember, at a turning point, derivative is always 0 anyway. You've done something like that in ITCSC. So if you are claiming gradient 1, it doesn't apply to that particular point. Do you understand? So that is why this interval will not be included. And that is where the problem comes. So let's see. Let's look at the derivative